Hello everyone, I'm Peter Kish, a second-year PhD student at the University of Warwick, and I'll be presenting my paper titled Deterministic Dynamic Matching in Worst-Case Update Time. And I would like to say special thanks to my PhD supervisor, Shayan Bhattacharya, and Tejal Sainarak for helpful conversations and hints regarding this project. We will be focusing on the matching problem, where our goal is to find a large set of vertex disjoint edges. And for clarity, we will refer to the maximum matching size of G as mu of G, as standard in literature, and we will say that the matching M is alpha approximate if it holds that its size is at least 1 over alpha times the size of a maximum matching. We will be considering the dynamic setting, where our goal is not just simply to compute an output for a given input, but we assume that the input undergoes updates over time, and our goal is to maintain an output during these updates. In the case of the matching problem, we usually consider edge insertions and deletions as updates. We want, for any dynamic problem, we could always just rerun our favorite static algorithm for the problem after each update, but we want to do way faster than this. When it comes to, so the goal in the dynamic setting is naturally to minimize the time it takes to complete an update, to calculate the appropriate output after an update. However, the way we measure this update time can be different. So the intuitive way of measuring update time is just simply considering the maximum time the algorithm might take to calculate an update. But in the case of some problems and some approximation ratios for the matching problem in particular, amortized worst case update time bounds are hard to be found. So we consider instead amortizing the update time over a series of updates, and we just derive an update time band over some banded series of updates. Clearly, a worst-case update time bound is superior to an amortized update time bound in this sense, and it is ideal to aim for worst-case update time algorithms, as they would yield more reliable algorithms in practice. The dynamic matching problem has been extensively studied. This is just a small survey of results, state-of-the-art results for the particular approximation ratios we will be considering here. And we will be deriving a few new results with specific approximation ratios in the with worst-case update time bounds through showing a general framework for improving specific kind of amortized update time band dynamic algorithms I call amortized rebuild-based algorithms to worst-case update time. The 3 new results we are deriving are 2 plus epsilon approximation in polylog update time, 3½ plus epsilon approximation in root n times polylog update time, which is randomized against adaptive adversaries, on what that means more later, and a deterministic algorithm for the same approximation ratio with a slight overhead of n to the lila of 1 compared to its randomized implementation. So what are amortized rebuild-based dynamic algorithms? Quite a lot of algorithms, specific in the matching problem, rely on the robustness of the output or the data structure they are maintaining. And the way to imagine that can be easily seen through a simple example. Assume we find a matching in a graph, a 1 plus epsilon approximate matching in a graph with our favorite matching algorithm. This can be done in semi-linear time using folklore algorithms. If we were to just simply wait for a number of updates, the matching we initially found would still actually be fairly good approximation if we would wait for a number of updates proportional to the matching size in the graph. And at this point, we could recalculate the whole matching and amortize the number of updates over these, amortize the cost of the static algorithm over these number of updates. And this would not give us anything non-trivial in terms of worst case update time, but could give us very nice amortized update time bounds. And the goal of this paper is to show how to transform these kind of algorithms to one which actually has very nice worst case update time bounds. Right, so to do this, we will introduce a different definition on update time, which was first noted the first observed by Danupon and Tachapal 2016. Essentially, what we are looking for here is a slightly stronger condition than just simply an amortized update time bound. So instead, what we do is not amortize the running time or the update time over the whole series of outputs or an arbitrary subsequence of outputs, but the algorithm can specifically define over which subsequences it is amortizing the update time over. So what I mean by that is that the algorithm, so for a given input sequence, the algorithm can specify that what subsequences will the update time be amortized over. If it can do it over k subsequences, we call it k batch dynamic for simplicity. And clearly, this is a stronger property than an amortized update time bound, well, and a weaker property than a worst case update time bound. Essentially, an amortized update time algorithm is a one batch dynamic algorithm, so to say. Right. So this was observed in the very same paper, but not explicitly stated, that if we can select k to be polylog n in magnitude, then we can design an algorithm which has several output tapes and maintains several outputs, such that at any time during the updates, at least one of these output tapes contains the correct result. However, even though it has more output tapes, it now has worst case update time, which is just a polylog factor larger than the underlying algorithm's update time. And in case of the matching problem, this is very nice because an output of a matching algorithm is a matching, it's obviously a matching, which is just a graph with maximum degree 1. Therefore, the union of a small number of such outputs is a very small graph with very small maximum degree. And in these graphs, these kind of graphs, there are already algorithms for finding an almost perfect matching. So essentially, we can, in parallel, maintain an output over all of these tapes in the case of the matching problem. Very briefly on how one should imagine this kind of transformation. I'm not going to expand on this in detail because it's not the result of this paper. Essentially, we just simulate the underlying algorithm on a number of output tapes while making sure that on at least one of the output tapes, the very last input element at any time is a complete batch of one of the sub-algorithms running on those tapes. And when a tape is not containing the correct solution, it is reversing some of its batches so it doesn't run out of batches to use. Essentially, the tapes are moving back and forth in time. More on this in detail in the paper and in the original 2016 paper, which introduces this concept. Now, so the idea is that an amortized rebuild-based dynamic algorithm can easily be turned into a k-batch dynamic algorithm. This is a core observation here. And how to imagine that? Let's just go back to the matching example. We similarly do the same thing as before. We compute a 1 plus epsilon approximate matching in semi-linear time, as we did before. And we want to make it now k-batch dynamic. So what we do is that we complete the rebuilds by a k factor more often. And whenever a new batch begins, we delay by the first rebuild by some factor. And what this ensures is that small subsequences the algorithm might choose as a batch will not contain a rebuild. And this way it guarantees that there will be sort of enough elements in every subsequence to amortize the update time if the update time is long due to a rebuild. The idea is simple as that. So this observation leads to a 4-step design for worst-case update time algorithm. First step, we need an amortized rebuild-based algorithm. We improve it to batch dynamic through this simple trick, which is more detailed in the paper. And we used existing works literature to improve it to worst-case update time, and we solve the problem on the union of the tapes because that is just easier to handle at the end. And this framework instantly will yield us two results. One of them is simpler than the other, since for 2 plus epsilon approximation, there has already been an amortized rebuild based algorithm. And to make it worst case, we just straightforward apply the framework described in the paper. That's easy as that. Now, we also receive a band for 3/2 plus epsilon approximation. However, algorithms for this problem were not, as far as I am aware, amortized rebuild based. So we will need a new algorithm. And once we have such an algorithm, we can just apply the framework in a black box manner. So as the core for an amortized rebuild based algorithm is a very robust data structure, which can withstand a number of updates while maintaining its output guarantee. And just to give an example, just to take the matching example as previously, as a matching is essentially a small number of edges, it is not very robust against updates. So the appropriate data structure for our purposes will be an edge degree constraint subgraph, which was introduced in a very influential paper by Merson and Stein in 2015. And if parameters are chosen well, it can withstand mu of g times root of n updates while still maintaining a good approximation ratio, assuming the matching size is large. And let's just assume that we can find such an EDCS, as it is not the result of this paper and it's fairly technical. I'm not going into what such a subgraph is specifically. Then if we would be able to find this in semi-linear time, and it can withstand about mu of g times root of n updates, if mu of g is comparable to the size of the graph, then we would instantaneously have a root of n or about root of an update time amortized rebuild based algorithm. But there are two ifs involved in this statement. So the two difficulties is that before this paper, I'm not aware of the existence of a semi-linear static algorithm for finding an EDCS for the parameters of our choosing. And it could also occur that the graph doesn't happen to have a large matching inside of it. It also requires consideration. So one of the results presented in the paper is finding such a semi-linear running time static algorithm for finding such an EDCS. And on a high level, this algorithm is just parallelizing the standard algorithms for finding a EDCS. So normally the EDCSs are found by putting about m edges in and out of an edge set we are continuously building. However, the time it takes for us to find these edges makes it so that we can't, or at least we don't know how to make this in linear time. Instead, what we do is that we kind of weaken the definition of an EDCS and we allow it to be locally faulty. And this way we can complete the same process through just a small number of passes through the edge set. And it will be working on the majority of the graph. And because it is only faulty on a small part of the graph, if the matching size of the graph is fairly large, we can disregard that small section as a slack parameter. So the slightly weaker data structure we introduce only works again if the matching size is large, which we will need for two different reasons now, but it does yield us a semi-linear time algorithm in the static setting, which is not true for a normal EDCS. Now, how are we going to guarantee that the matching size of in the graph is fairly large? Well, there's a very standard attitude or approach to guarantee this for us, which appeared in a number of works, but I think first in Asadi 2019. The idea is simply to contract the vertex set in such a way that we preserve a large portion of a maximum matching. So we guarantee that it's in contracted vertex set, we can still find a maximum matching. On a very high level, let's just assume that the graph has some n nodes and we contract it to mu of g over epsilon vertices. we can assume that we know mu of g because we can guess it within 1 plus epsilon accuracy with running log n over epsilon parallel copies of the algorithm. And once we did this kind of contraction, any edge of an arbitrary maximum matching will survive this contraction step with very high probability, with about 1 minus for the epsilon factor. So we are not losing much of the matching through the vertex contractions. And we can work on this friendly size graph from now on. Now, there's a slight issue with this existing approach, is that after these vertex contractions have happened at initialization, some updates might come which are dependent on which vertices we have chosen to contract and ruin the maximum matching in a contracted graph, while might not ruin the maximum matching in the original graph. So this aptitude doesn't work against so-called adaptive updates, where the adversary who's completing the updates is aware of the random bits of the algorithm has chosen. So we solve this problem through running this vertex contraction step a number of times in parallel. And what we are going for here is that we want to guarantee that regardless how these contractions happened and what edges are deleted from the original graph, in one of the contracted subgraph, any maximum matching or most of any maximum matching will still exist. What we find is that if we take a small number of completely random vertex contractions, by small I mean polylog number of parallel vertex contractions, then we are already happy, because in one of them with high probability we will have a well-preserved maximum matching. And this is essentially robust against an adaptive adversary, since the randomization happens at the start of the algorithm and works with high probability on any kind of input which comes afterwards. On the other hand, this is inherently randomized, and we would like it to be deterministic for the sort of sake of completeness. And we show how to do this through basing the constructions on the edge sets of specific expander graphs. However, the existing algorithms for designing such expander graphs will require us to introduce an n to the little of 1 overhead, and that's why we get this O hat of 1 blow up, unfortunately. Okay, so these are the core ideas of the paper. There's many smaller steps building up a framework, and the small steps separately make sense. They're very independently presented. And this results in a number of possible research directions, at least I hope. So the EDCS concept, or matching sparsifier, was very influential, and it has found a number of applications. It has found applications in different settings, such as streaming as well, not just dynamic and static. And this version of it, which is sort of locally damaged and therefore is easier to be found, might have some applications. The framework we present here only uses the fact that we are working with a matching problem. The only way it uses the fact that we're working on a matching problem is that we assume that we can find a solution in the union of the small number of output days, which is true for the matching problem, but it is true for other problems as well, which means that it might have applications outside of the matching problem. And I also think that this sort of new method of vertex construction, which works against adaptive adversaries or even in the randomized setting, might have applications for the matching problem in different settings, because it allows us to deterministically assume that the matching size in the graph is pretty much the same as the size of the graph itself within some select parameters. Thank you for listening.